Hello, welcome back. So today I thought I would do a sidebar on Fourier Transform because we are going to want to have a Fourier Transform in our Synth at some point in the future, and so it should be good to get an understanding of this really useful tool. So what is a Fourier Transform if you haven't heard of one? Well, usually, you know, when we're having our synth, we have our signal, which is a bunch of samples. So if I draw a graph here, right, where the x-axis is time and the y-axis is the amplitude, or you can think of amplitude as the air pressure, then our signal is just, you know, something like this. It's a change in pressure over time. And this specific change of pressure, when we perceive it, we perceive a certain tone. So for example, this might be a 4 Hertz tone. What a Fourier transform does is it transforms this information, transforms it into a different graph, where now our x-axis is our frequency, and the y-axis remains the amplitude of a specific frequency. So you can imagine if along the x-axis, you know, we had 0 Hertz, 1 Hertz, 2 Hertz, 3 Hertz, 4 Hertz, 5 Hertz, then when we do this transform, what we expect to see is a spike here at 4 and 0 everywhere else. Now in reality, what we actually end up seeing is more of a curve around 4, due to the uncertainty principle, and I'll try and get in that. But basically, how certain we are about a certain frequency depends on the number of samples we have, big N. So the more samples we are able to analyze, the more certain and sort of this curve will squeeze in and become more and more like a spike. Obviously, if we're analysing just a short amount of samples here, then we're going to get a larger curve representing a larger uncertainty over what the frequency could be. So how would we even go about doing this? And I just want to say, we've already done a Fourier transform. So if I come over to Audacity, we were using Fourier transforms already when we were analysing some tone. So if I come here and generate a tone, we'll generate 440 Hertz, which remember is note A4 on the piano. 1 second. So here's our tone. Well, Audacity has this where it says, if we come to the Analyze menu and plot spectrum, this is doing a Fourier transform. This is transforming this signal, which is referred to as a time domain signal, into a new type of signal, which is called a frequency domain. And you can see this is what we get. At 440 Hertz, we get this spike, and everywhere else is 0. So how can we go about implementing something like this? Sorry. Well, let's look. So if I clear all this again, the naive way to do it, and that's how we're going to do it first, is we're going to chop the wave up into chunks. We're going to chop our incoming signal into chunks. So you can imagine if we put an equally spaced cut here and here, and then what we'll do is once we've cut up our signal, we'll overlap them. We're going to overlap this piece onto this piece, and what we end up with, if I draw another thing here, now I'll lower the opacity. So our piece, so we'll call this piece 1 and piece 2. So piece 1 will look like this, and if we overlap piece 2, you'll notice it'll just overlap nicely. And if we sum the result, we're going to get this much more exaggerated wave. Now it just so happens that we've spaced our cuts, so this is our cut here. We've spaced our cuts such that we're cutting 4 times a second. So with our cut frequency, we'll call this our cut frequency. The cut frequency is 4 Hz. And the actual signal's frequency is the same, 4 Hz. Then obviously they're going to overlap nicely. Now if I, let me undo all this. What happens if we cut at a different rate? Say, you know, we cut here, here, here. So these cuts are much more packly tight together. So you can imagine that something like this is, you know, maybe 6 Hz as opposed to 4. Well, what happens when we now try to overlap these? Remember, so this is piece 1, piece 2, and piece 3. So we come and we try and overlap piece 1, and then piece 2 overlaps like this, and piece 3 sort of starts here, comes down like this. And you'll see they don't overlap nicely when we're at a different, when our cut frequency is different to the actual wave shape's frequency. And usually what happens is if you then try and take the summation of this, you try and add all these overlapping waveforms together, we end up with silence. So this is really what a Fourier transform is trying to do. One way to do it is instead of trying to figure out what are all the frequencies in our signal, we can just ask one question: is the frequency 4 Hz in the signal? And we test for that. And then we ask another question: is 5 Hz in the signal? We test for that. Is 6 Hz in the signal? We test for that. And the way we test for it is by changing the frequency of these cuts. So let me show you a demo. So I've written a bit of code for this. It's very similar to what we've all been doing in the coding a synthesizer in C. So here's our main function. All we're doing is we're using raylib as usual. We're opening our init window. Our state here, so if I come up to the top, our state just has 2 arrays, one that will hold our signal and one that will hold the Fourier transform. And then here in update, we're generating the signal, and you'll notice we've done this in the synthesizer video, where to generate a sine wave, we take the sine, it's 2 pi times the frequency, and then we want to times it by the index of the signal divided by the number of samples in that signal. So this normalizes the whole thing to the 1 second range. So, and all this is just, I've added some UI stuff so we can change the frequency on the fly. I mean, we're doing this 3 times so we can have 3 separate frequencies. But for now, we'll just look at one. I've set frequency 1 to 4 Hz and the other to 0, so they'll have no effect. And then if we come down to our draw function here, all we're doing is we're drawing the signal. We're just looping over each sample in the signal and drawing a pixel on the screen for where that is. And then we're doing a cut here. So here's our cut frequency. At the moment, I'm just setting the cut frequency based on the mouse. So when my mouse is at the right side of the screen, it's going to be cutting at 10 Hz. And then at the left side of the screen, it's going to drop down to 0 Hz. And then drawing the cuts is pretty easy. We set up a cut stride. So this is just how many, by dividing the number of samples by our cut frequency, we can figure out how many number of samples do we need to jump each time to cut it. And then we're going to draw it. So let me compile this, make sure it compiles, run it. So here we go, here's our signal. So here's our 4 Hertz signal. Obviously I can change the frequency to be higher or lower. And as I move my mouse left or right, I'm changing this cut frequency. These green lines are where we're cutting it. So we're going to want to modify this now. I want to be able to show how, how I did in here. We want to show how it overlaps. So I'll add that. I also want to see what the actual cut frequency is, so I'm going to draw that in the corner. So let's do that. So let's draw, I think it's just draw text, and then it'll be text format. I'm going to call this cut frequency. And then we're going to draw that up, sort of just that like 15, 15, and just in white. Oh, and the font size will be 20. That looks like it's compiled, and here you go. We can see, and just to be absolutely clear, this is in Hertz. So here's our cut frequency. As you can see, on the right side it's 10. So now we're going to want to draw the overlap. And that should be pretty simple. I've got my to-do here, draw the overlap. So we've got this while loop here, where within this while loop, we're adding the cut stride to this cut X position. And we're drawing the line, that green cut line each time. So we want another loop in here where we loop over all the samples in those cuts and then overlay them in the same region. So how I'm going to do that should be pretty simple. I'm just going to say n equals 0. So we're going to want to say, while n is less than our cut stride, so this is going to be a relative n plus plus. And we're probably also going to want to say because we could end up trying to read a signal off the screen that we don't have, so we need to account for that case. So we're also going to have to say, and n plus our cut X is less than the number of samples. Then we're going to get our sample. So that's going to be easy. It's in our state signal, and we're going to get n plus cut X so this is going to get us let me show you. It's going to get us all the samples within these 2 cut bars. And then we want to draw that. We want to draw a pixel. So our X is just going to be, where do we want to draw this? Let's just draw it after the first. So cut stride plus n. Our Y is going to be starting at our signal baseline Y plus the sample. And then I'm going to scale that to our signal height, so it matches up to the height of our normal signal. And then we're going to give it our signal color, which I've already defined up here. And that's it, I think. So let's make sure that compiles. It does. And here you go. You can see it's now overlaying. Hopefully you can see that clearly. So you notice as I sweep this cut frequency, as I change the width of these cuts, sometimes we get a mess, and then sometimes it tends to resonate. If I come here, and you can see as I approach 4 Hertz, they all line up and it perfectly resonates exactly at 4 Hertz. And then as I go past 4 Hertz, they start to defocus again. and it becomes more messy. But you'll notice there are other sort of, it kind of resonates here, but you can see if we were to sum this up, the positive bit would cancel out the negative bit, and that would just be 0. So what I want to do now is I want to draw that summation. So here it is, here's my to-do, draw summation. I'm going to draw this before we draw our text. So how are we going to do this? Well, we're going to have to create another array for this. What I'll do is create a new, I'll call this our summation, and this is just going to have the same number of samples in it. I'm going to 0 that out. So this should be pretty easy. All we want to do is we want to say summation n plus equals our sample. Right? And then to draw our summation, we'll have to do another loop. So we only want to draw the summation within that cut region. So we're going to draw up to our cut stride, n++, and then let me just copy this. So this just becomes our summation. And then we want a, we'll do the cut color for this. All right, let's compile that. Compiles. And here we go. We've got our summation here. So if we start over here and we start to sweep, notice as it comes, things come in and out of phase. It will sort of wobble back and forth. But when it resonates, we get a nice big wave here. There's our resonant bit, and then it comes out again. Remember this bit here where it was even on the top and the bottom, and we get just a blank line, we get silence. So that's pretty cool. Let's see if it works for other frequencies. Let's try 5. What happens when we get to 5? So you notice, if you look at the cut frequency in the upper left corner, it's detected at 5 Hz. So this is a very naive Fourier transform. Effectively now what we would want to do, let's try 7. Now you notice at some points, here we go, there's 7. But let's try 6, and then now notice here we've got 6. So if we come to 6, obviously it resonates at 6, but it also kind of has a bit of a resonance at 3, and that makes sense, right? Because 6 is a multiple of 3, and same at 2. We get a bit of resonance at 2. Notice it's not as strong as the resonance at 6. 6 is the strongest. Then 3 is weaker, and then 2 is weaker still. So what we're going to want is to also take into account the width of our cut stride. And we kind of want to say like the smaller our cut stride is, the more confident we are about that frequency. So 2 resonates, but the cut stride is a lot longer than here at 6. So this is why I was saying this is a naive version of the Fourier transform. Let's try it now with multiple frequencies. So let's bring in 1 at 4. So you'll see now, ooh, oh, I think I need to account for when we go below 0. We do account for that here. Oh well. Let's do 4 and 6. I think what the problem is, our cut stride is greater. No, that's right. Greater than 0. We'll just make sure that our cut stride is always at least 1 sample long. That way we won't run into that problem. Or we will. When it gets below a certain point, we're getting I think an array out of bounds error. I don't know if it's could be this. Yeah, it's our summation code. So let's have a look at our summation codes. Our summation n, while n is less than cut stride, really we want to do min cut stride num samples here, whatever the smallest. There we go. So yeah, I'm going to do a frequency at 4 and a frequency at 6. So we'll get a much more complicated waveform here. So let's try this again. So we get a little bit of resonance at places. So here we got some resonance at frequency 2. Makes sense. 2 is both a multiple of 4 and 6. Or a factor, I should say, of 4 or 6. But as we approach 4, the key point here is we just get 1 cycle. We get a resonance of 1 cycle. You can also think of this as a standing wave. We get a fundamental standing wave here. Whereas before, you know, there's 2. This is the second, I believe you would call this a second harmonic. So at 4, we get our first harmonic. Same with 2, if we come back to a cut frequency of 2, we get a much more complicated harmonic. But at the places where we've actually set our frequency, we get fundamental harmonics. Even though now that the structure of the wave is more complicated, sort of see here how it overlaps. And let's bring in an even higher frequency, let's say 9. So it's more complicated still, but as we approach 9, you know, you can see it. Even though the overlap structure looks really messy, it just so happens that when you sum those all up, you get a fundamental harmonic. Same with 6. And the same with 4. So yeah, like I said, what we want to do now is we want to have a loop that automatically sweeps through all the possible cut frequencies and tries to detect for these harmonics, these resonance. So turns out there's a nicer way to represent this than just doing this method of cutting it up and then sort of overlapping them on top of each other. And the way to do that is by wrapping it around a circle. And I'll try and explain. So if we come back to our drawing thing here, so the actual formula for a proper Fourier transform, I've got it pre-written down here already, is this. Now, don't be too afraid, I'll try and explain it. But first of all, I just want to bring your attention to this bit here. Let me change my opacity. See this bit? Ooh, my tablet's playing up. Come on. 2 pi times some number where n over n. This is how we draw a sine wave, right? Our sine wave is usually sine 2 pi times our frequency times t over our rates. So it's sort of t over what do we call it? Our sample rate. Call this SR. Right, that's basically what this n over n is. K in this is just our frequency. So K is our wrap frequency here, or our cut frequency. And then this term just sort of normalizes the whole thing into a 0 to 1 seconds, right? And then the 2 pi makes it so every 1 second we go around the circle, 1 full revolution. Right? So we already understand this bit of the code, this bit of the formula. We've done it. We've done it multiple times before. So what is going on with everything else? Well, I did say we need to create a loop now where we go over each cut frequency and sum them up. So in this case, x of k, so x of n here, let me go to green. So this is our signal, right? X of n, this is basically when we were doing signal brackets n, right? X of k now, this is going to be our Fourier transform. This is going to be our Fourier transform. Okay. So what we're going to do is, this is the summation operator. So starting at n equals 0 up to big N, which is basically our num samples. Right? So this whole thing here is basically our for loop, right? We're going to take the sample, and then we're going to multiply it. Now this, if you've not seen this before, can be confusing. And this brings us to, this is Euler's formula. So what is going on here? Well, to understand this, we sort of need to learn about complex numbers. So essentially, we've got a number line. Yeah, come on. There we go. So we've got a number line. So we've got 0, 1, 2, -1, -2. Complex numbers adds a second dimension to the number line. But the question is, what numbers do we put in the vertical axis? Because we can't just use these numbers there for the horizontal one. So mathematicians introduced the notation of I. So here's I, here's -I. Then we just do 2i, -2i. So, we know if we had a number at point 1, we'll call this x. And if we did x minus 2, well, that would move this point to here. Now the question is, now that we've introduced this vertical axis, how do we move points into the vertical axis? Well, just the convention is, and again, this is a convention that mathematicians invented, is to use e to the I. E raised, so this is the exponential constant, raised to the power of I. And what this does is it rotates the point 90 degrees into the vertical axis. If we did e to the 2i, this would rotate it a further 90 degrees back onto the... So x minus 2 is equivalent to x multiplied by e to the 2i. Now there's a second way we can represent this. We don't have to use this notation. If we want to draw a circle, you can draw a circle if we use just like an xy coordinate pair. Then we just say like x is equal to sine of our angle, and y is equal to our cosine of the angle, right? This is another way of representing a two-dimensional circle. So we could use this layout, and I think we'll just use sine and cos. But go ahead and try and go online and read up about it. It's called Euler's formula. And you'll also hear sometimes Euler. Sorry, I should call it Euler's, not Euler's. Euler's identity. So these are two. Just put these into Google. But what I'm trying to get at is this sort of Euler's formula is just the same as doing something like this. Right. So one other thing I want to say is there are other people out there who could probably explain this a lot better than I can, because even for me, this is on the very edge of my sort of ability with mathematics. I am not a good mathematician at all. But if you want to check out a channel called 3 Blue 1 Brown, let me get past the adverts and then I'll bring the tab over to this monitor. Yep, so Free Blue 1 Brown is an excellent YouTube channel that explains various mathematical concepts. So they've got a video on there that's explaining various, geometrical ways of looking at the Fourier transform. And you can see this top bit, it's a bit like what we're doing now, where they've cut the frequency into slices. So I highly recommend this. It's called, channel's called Free Blue 1 Brown, but what is the Fourier transform, a visual introduction. Highly recommend this video. All right, so we're gonna do something like this. So if we come back to our code, what we want to do now, and we've done the overlap, so we can done the summation. So I'll just call this your summation. Draw overlap. We now want to draw circular wrap. So what I'm going to do now is, keeping those cut lines, I'm going to use those cut lines to wrap our signal around a circle, such that within a cut region, that bit of the signal will wrap around the whole circle one cycle. And then the cut region next to it is going to wrap around it again. So how can we do this? So to do this, we're going to have to loop over we're going to have to do this again. We're going to loop over all our samples. Well, what we're going to need to figure out is what is the, two coordinates, because we're drawing a two-dimensional object now, a circle. So, like I said before, we can do like sine of n, cosine of n, right? This will draw where n is our angle, so I'm going to introduce a new variable here called theta. And a new variable here called magnitude. Let's just say, I don't know, 50. Oh. And then we're going to draw a pixel and our x and y. We'll draw it the same as our cut color. And then I'm also going to want to bring the x into the middle of the screen, kind of. So we'll say 512. Let's put it at 400. So make sure that compiles. So here we got a signal, and if we wanted the signal, we got a circle. If we wanted the circle to be bigger, we just change the magnitude here. We got a bigger circle. I was pretty happy with, maybe we'll do like 75. So now we want to sort of take our signal and wrap it around this circle. How do we do that? Well, that should be pretty easy. We need to get our sample as usual, which is just going to be n. And then we need to change the magnitude, right, based on n. So we could do times our sample, right? But what we now need to do is maybe also change the theta. So at the moment we're wrapping so how can we do this? because we're setting theta to n, and obviously n goes past pi multiple times. So that's why we're getting this structure. It's sort of, oh, what do you mean it's used by another process? It's wound around that circle really tightly. I am going to make this a bit bigger actually now. So just by dividing n, just by converting this into a float and dividing that, say, by 10, we can wrap it, we can make the windings less and less. But we want this to be a function of our cut frequency, right? So I don't know if it's correct to just multiply it by a cut frequency. We'll have a look. So I still think that's a bit too much. So we might also need to divide this by pi. You know, this whole thing. Oops. Or divided by 2 pi. I mean, we get some pretty patterns. I did create a backup here where I've already done some of this before. Right, yeah, that makes sense. So basically what we want to do is we want like a normalized version of n. So at the moment we're getting n going from 0 to num samples, which is 1024. We want that to be normalized between 0 and 1. To do that, we just divide it by num samples, right? And then our theta basically becomes 2 times pi times ns times our cut frequency. Sorry, I had a complete brain fart, because if you look at this now, look, 2 times pi times cut frequency times n over little n over big N, basically. And we just looked at this. This is this right here. 2 times pi. K is our cut frequency. Little n over big N. That's our index over the number of samples. Okay? So that compiles, and here we go. This is exactly what I wanted. I am going to make that a little bit bigger still. Let's do 200. So here it is, and this is what it looks like when we try and wrap that signal around the circle. We get some interesting patterns. And it's a very easy way to see the number of harmonics. So you can see here it's resonating with 3 loads, which means it's a third harmonic. Here there are 4 loads, 4 harmonics, right? And as we approach 4, we should just get 1 load, which is a fundamental harmonic. And then as we move away from the actual frequency of the signal, you can see it sort of shifts out of focus. And here's 8 Hertz, which is double the actual frequency. you know, so we get some interesting shapes. So let's bring in, you know, maybe 5 Hertz. You know, 4 and 5 don't divide into each other quite as nice. But if we come to 4, so obviously the loads now aren't quite as clear, but you can sort of see that all the loads are on one side of the circle. And if we come to 5, again, all the loads are on one side of the circle. Let's bring in frequency 2. As we come down to 2. So now they're not all on one side of the circle. You can see there's some on the left side. But you could sort of see, if we were to sum all this up, it's heavily weighted towards the right side. And in fact, that's what we're going to do now, is we're going to take all these points and add them together. So now we're not just doing a summation in one dimension, we're doing a summation in 2 dimensions. And what that does is it sort of takes like the center of mass of this circular structure, except it's not quite the center of mass, because if we were to do the center of mass, we would sum them all up and then divide by the number of points, and that will give us the center of mass. But we're going to leave out the divide step. We're just going to sum them all up, which means we could end up with a center of mass way outside the actual structure. And I'll explain why we leave out that division step later. So let's try this now. So here's our circular wrap. Again, we're going to want to have 2 variables now. We want to sum up the y-axis and we want to sum up the x-axis. And this is pretty simple. Before we add these baselines to it, I'm just going to say sum x plus equals x, sum y plus equals y. There we go, we've done the sum. And now we just need to draw. We'll draw the 2D summation. So for this, I'm going to draw a circle. And that's going to be, we do have to cast these back to integers for the pixel positions, but it's just going to be sum x. We probably want to move these up, so we'll say our circle origin x is equal to 512, circle origin y is equal to 400, and then we'll just do this here, circle origin x plus circle origin y. These can go. Sum y plus circle origin y. We'll make it 20 pixel radius, and let's create a new color for this. We'll say yellow, and this will be our I don't know what to call this, to be honest. This is our sum 2D color. So this will be our sum 2D color. Let me make this a little easier to read. Let's see if that works. Okay. A, too big. B, too far. You can see adding all these points up moves it out way too far. So we need to divide this, or we'll times it by some. We'll call this F32 some 2D scale. So, way too much. Let me change by 1 order of magnitude. And there we go. So now you can see here, again, the actual signal is 4 Hertz. And notice as we change the cut frequency, look at that, it comes all the way out here. So I'm actually also going to draw a line. From our circle origin and circle origin Y to this. So I'm just going to say this is the sum x final. I'm just going to pull these out. Then we're missing a semicolon. There we go. So you can see the length of this line is what we're going to plot on our Fourier transform graph. So let's bring in 5. So again, as we approach 5, and notice it always happens on the right side. When the line gets long, it's on the right. So we come to 4, it's on the right. Whenever there's other sort of resonant places, let's see, maybe 2, there should be one at 2, right? So, I mean, this is interesting. We can see when we do the naive method above, when we were just overlapping the cut pieces, you know, we saw some resonance there, but then when we look at the sort of the circular representation, the sum is in the middle. So let's bring in 6. So yeah, I wanted to show you this example here. We do get one where it comes far out, but it's pointing up this time. And then when we come to 6, it's pointing to the right. So there's some information encoded, not only in the length of this, but also the angle, the direction in which it's pointing. You know, if we come to 3 again, 3 is a factor of 6, and it's in the middle. You know, if we cut out the 5th frequency, so doing this circular method, it sort of cuts out the problem of having those multiples or factors of our root frequencies. Because our yellow dot, it comes back to the center. So let's try something now. So I showed you before how, if we come back to 4, we go to our cut frequency of 4. it's pointing to the right. What happens if we change the phase of our frequency? And changing the phase is pretty easy. So I'll just change the phase of the first one. If I change this from a sine to a cosine, that's going to offset the phase by 50%. Or offset the phase by pi. So let me compile that. And let's come down to a cut frequency of 4. And look, now it's pointing down. It's 90 degree, the direction is offset by 90 degrees. And this would be true for the other frequencies as too. If I come down to 2, or would it? Oh no, of course, because I only the first frequency we did cosine on. The second frequency, which is this one here, it's still using sine, so we come to 2 and it's pointing to the right. Then we come to 4, it's pointing down. So the final thing to do now is to turn this into a plot. So essentially now we need to loop over all the possible cut frequencies and plot them. And plot, we don't want to plot the distance. Basically, we want to plot its x, right? We want to project this yellow vector onto the horizontal basis. Because for now, we only care about frequencies with no phase offset. So how do we do that? Well, let's do this. We're going to create a new function up at the top. DONWLOAD. We're going to call this our slow Fourier transform, because possibly in a future video I'll talk about how we can optimize this and do a fast version. And this is going to take in a signal. It's going to take in the time domain and output the frequency domain, right? And we also want big N, or no, we'll call this size, the size of the number of samples. And we basically need to copy what we've done here. So we first of all we do for each sample so for now we'll just say our k, right? We're gonna reuse the terms from this. So our k here is equal 1 Hertz. So we're going to want this wrap bit here. So I'm just going to come down here and copy this. Oh, I did not copy that correctly. There we go. Let's copy this in here. We're going to want our sum x, some y. We don't want to do that scaling anymore, right? So cut frequency becomes k, ns becomes n over size. Our signal just becomes our time domain n, and then we want to say sum x plus equals x, sum y plus equals y. So then we're going to want to wrap all of this in another loop where we step through. So this then becomes 4. And then the other question is sort of what range do we want our frequency domain to be in? For now, I'm just going to hard code that from between 0 Hertz to 10 Hertz. So I'll do 4, I32. I don't know what to call this variable. I'll just call this ki, k index. Well, ki is less than size, because these two will always be the same size. Ki plus plus. Right, and we're going to wrap all of this in a new loop, and then k would just be, we're going to normalize this, right? And then multiply it by the highest frequency. And then all we do is we just say our frequency domain is equal to, and right now we're going to ignore some y and we'll just do some x. We'll just look at the sum x, right? And that's it. That's our slow Fourier transform. And the reason it's slow is because you can see here we're looping over all points in size, and then there's another inner loop with all points of size. So the complexity of this algorithm is O to the n squared, right? And maybe in a future video we'll show how it's called FFT, which stands for Fast Fourier Transform, can do this into O n log n, I believe. I might be wrong about that. So I'll just put in a 2 to make a optimized fast Fourier transform. All right, so we need to do this. We'll come down to our function here. So we'll do our slow Fourier transform. We need to pass in our signal, right? And then we need to draw, or we'll say draw the frequency domain. And that's going to be very easy. Again, and then we just need to get the, we'll call this f, and we're going to get state.Fourier transform n, and then we just need to draw a pixel of that. So x will be n, pretty simple. Y is just going to be f. We might want to times that by something, I don't know, 100 pixels. We're going to want to draw this towards the bottom of the screen, so let's draw it at 650. There we go. And then we'll just use the sum 2D color, right? Let's make sure that compiles. Oh, I guess we just need to give it a pointer to the first index. So we actually times that way too much. I believe it's inverted, so we'll do a negative there. And there we go. And if we look here, this is our Fourier transform, and we get our spike at 4 Hertz. And as we increase the frequency, this increases. Let's bring in another frequency. You know, if we did 2 frequencies on top, the same on top, we just get a bigger spike, because remember, the x-axis is frequency and the y-axis is amplitude. So here's 8 Hertz, and if I move the mouse on top of this one, we get 3 Hertz. There's 1 Hertz. So you can see this is working a lot like how it did in Audacity. If I were to generate another tone at 220, is there a way to mix these? Tracks, mix and render, there we go. And then if we analyze, you know, a similar thing where we get 2 spikes. Now, the one in Audacity is doing a little bit more analysis to remove some, and don't forget there's a lot more samples as well in Audacity. There would have been 1,000, that was 4 seconds long, I believe. So at 44, you know, actually no, I think it's at 48,000 sample rate. That's how many samples it's analyzing. Whereas we're just analyzing 1,024 samples. So this is why we get like these ripples here, because we just don't have enough information to be entirely certain about the frequency, right? Which is why the width of this peak here is quite wide. But you do notice as we start to stack the same frequency on, it gets higher and a little bit narrower. So that's Fourier Transform. Yeah. I wasn't sure I'd be able to get through this and explain this. I did do a bit of reading up on Fourier Transform before. To be honest, I was myself quite scared of jumping into this topic because, like I said, it is at the limit of my mathematical understanding. I'm by no means any good at things like algebra and calculus and complex numbers. But just the act of doing this practically and coding this out, I think is a really great way to understand things like this. And I gotta say, the Fourier transform is a really beautiful formula. And when you learn about it, you'll see it has so many different uses, not just in audio, literally everywhere. It gets used in quantum physics, gets used in all types of signal processing, not just audio, but electronics. It gets used for sort of stealth, you know, and radar detection. Yeah, definitely read up on the Fourier transform. It's pretty cool. So now that we've got this, we can bring this into our synth video, our synth series, and use it. For example, we can make an equalizer with this by doing a Fourier transform, and then we can just manipulate the graph in the frequency domain to say boost the frequency or reduce the frequency, boost the mids, lower the highs, and then we do an inverse Fourier transform. And that's very easy. It's practically just putting it back through a Fourier transform with one slight minor tweak. Basically, instead of going around the circle clockwise, we then want to go around the circle anti-clockwise. And that inverse Fourier transform takes the frequency domain back into the time domain. So yeah, that's Fourier transforms. I'll probably do another video for the FFT at some point. But until then, goodbye.